Welcome to this NPTEL lecture on principles and techniques of modern radar system. We are continuing our discussion on resolution, ambiguity, etc. So, we have seen range resolution in the last class. Today, we will see the velocity resolution. Actually, you know that velocity is measured by Doppler shift. So, sometimes it also is called the Doppler resolution, but I prefer this term velocity resolution because actually you are measuring velocity. So, let us say for we know target radial velocity if it is v, I am not writing Vr. So, we know the Doppler shift is 2 v f c by c. So, now let us say again I have a stationary target, and let us say that its pre-envelope is phi t. So, let me write because it will be easier for you. Pre-envelope is psi t for this, and so its Fourier transform. Let us take its Fourier transform, because since the concept of frequency is coming. So, unless and until we go to the Fourier domain or frequency domain, we will not be able to see the Doppler shift. So, let us make the Fourier transform is psi f. Now, this is psi t. Actually, I should have taken a different symbol for denoting the Fourier transform, because this thing and Fourier transform are completely different functions. But if I do that, then this is the Fourier transform of this time function, that sometimes gets obscured. That is why we continue that, but please remember that this psi and this psi, they are not same, though we are using the same symbol, but actually they are different things, because this thing may be real, but this is the complex. So, this is a completely different function and it is basically integral thing of this. So, all those things all of you know, but sometimes we forget that is why I am remembering. So, what is this? This I can write from my knowledge of Fourier transform, that this is psi t e to the power minus j 2 pi f t, this is d t. Okay. Now, instead of stationary target, let me go to moving target. So, in case of moving target, the received signal spectrum will be shifted by f d. So, the pre-envelope becomes that time psi f minus f d. Okay. This is now, let us consider as before that I have two targets with velocities v1, radial velocities with radial velocities v1 and v2. I am not writing Vr, but obvious it is radial velocity v1 and v2, and they are at same range, because when I am studying the velocity thing, I should make the range equal, otherwise that will complicate. Later we will remove that restriction and make everything may change. So, and at same range. So, the returns, the pre-envelopes for them, one I will be calling, or let me call like this, that. So, one will give me return f minus f d 1, another will give me f minus f d 2, because V 1 will give me f d 1, V 2 will give me f d 2. So, I can now form that integral square error, but to remember that this is in the frequency domain between two such Fourier transform things. So, I am writing f as a subscript, and I can form again this difference integral square error. So, this is phi. So, again I can make any of them as a reference. So, let us say that our reference is f d 1, f d 1 is the, let us say, reference, and then without losing generality I can make this f d 1 to 0. So, basically we will be dealing with their difference. So, that is delta f, but to say that it is the Doppler difference, I will use the symbol f d. Again I am repeating that. So, I will get pre-envelopes like this, but this f d 1, let us take f d 1 as a reference, and then the difference between the two in Doppler will be delta f or delta f d, you can say, and that I am calling f d. So, that means in our now f d means the difference of Doppler between the two echoes. So, I can form this thing, that means from this first target I am getting the pre-envelope psi f, and from the second target I am getting f minus f d, okay, and I am forming their integral error like this as before. So, this thing I am not going into the details, the same way you can manipulate. So, we can finally I can say that to have this square minimum I should maximize to minimize the square error. Ultimately, I will have to maximize real part of minus infinity to plus infinity psi f star psi f minus f d, this d f, then real part. So, it is this. Okay. Now, please see equation 13, because that was the definition for this thing, that relation between the pre-envelope and the complex envelope. So, equation 13 I am just again writing, you need not. So, you can refer to your equation this thing. This is the definition of pre-envelope, relation between pre-envelope and complex envelope, but this is in time domain. Here I have got this psi f type of thing. So, I need to take Fourier transform of this. So, I can say taking Fourier transform, I can write psi of f will be f minus f c. This is a shifting property, I think all of you know. So, this thing I can write that we need to maximize real part of minus infinity to infinity psi star f or I can directly put in terms of x. So, maximize x star f minus f c, then is f minus f c minus f d then d f. So, this thing you see, it is called, actually this is again we are coming to a correlation type of thing, because this is nothing but a correlation function. So, that is called, I define it like this, x f f d is minus infinity to infinity and this thing if we do in time domain, then you will get it simply that so this is an important thing that, and this function is called frequency correlation function. So, we should give it again an equation number 38. So, what we see that this I will have to maximize this correlation function to resolve or not to resolve. That means, again the ideal thing is if this correlation function goes to peak at f d is equal to 0, that means no relative Doppler shift between the two targets, it should go to very high value and near that it should fall again, ideally delta function, but again that is not possible in nature. So, I should again require that if I have this plot of this frequency correlation function magnitude, then that should have a peak, actually the peak is also here. So, here I am plotting the relative Doppler shift and near that it should have a peak something, and then I do not know the shape, but it should fall very fast and it should fall with a high roll up, so that I get a very sharp thing. So, this the falling that width, that will be called the resolution. So, if I call it delta f d, that is the resolution. So, from the graph again the same concept, and so we can get that delta v, the velocity resolution, that will be c delta f d by 2 f c. So, this is our velocity resolution, ultimately what we are looking for. So, I think we should give it a number, equation number 39. So, again the Doppler resolution. So, it will be determined by a thing. So, now you can choose, because you see everything depends on the shape of x t. So, x t designers can choose, so that to give both this range ambiguity function and frequency correlation function a sharp peak at the respective 0 values and a very high roll up, so that the width is. So, now we will make that combined, we will combine these two, because while making the understanding the range ambiguity function, we made the Doppler shift 0, that means the velocity 0. While making velocity 0, we made the range 0. Now, we should combine them. So, I will call that the combined range and Doppler or velocity, let us say. So, this will be now. So, again I will now hurriedly go that the pre-envelope of the transmitted waveform, let us say it is x t as before, and then the what will be the pre-envelope of the time delayed. So, pre-envelope of time delayed and Doppler shifted echo so that will be psi t minus tau, that is x t minus tau e to the power j 2 pi f c minus f d and t minus tau, as simple as this. So, again utilizing the previous two concepts, that so now I can form again this integral square error. This I am not giving any subscript now, because it is the general thing. So, epsilon square, that will be minus infinity to infinity the first one minus the second one. This is the return from the second echo, this is the first echo. Appropriately we have taken the references. In one case the first one range that has been taken as reference, or the first one time delay that has been taken as reference. In the frequency also the first Doppler shift has been taken reference, and both of them, that means the first time delay for the first one and the Doppler shift of the first one, they have been without loss of generality assumed as 0. So, I am writing like this, and t minus tau square d t. So, this can be, again you can easily manipulate that this I can write directly as 2 minus infinity to infinity psi t square dt minus 2 real t minus tau dt. Now, you can put those values as given here, and if you manipulate, you will see that here a j 2 pi f c minus f t tau into this integral term, that x t x star t minus tau e to the power j 2 pi f d t dt. You should close this. Okay. So, you see that it is again the correlation function, but there is a this Doppler shift here, and here previously it was just a phase dependent or tied to carrier frequency. Now, it is f c minus f d. So, again you need to maximize this. So, to have good both the good range resolution and good the velocity resolution, then again we require that this integral function, the function under this integration, that should be maximized, and then we will have a. So, now is the time for defining a function for this, that we define it, very important function, and you see this function is a 2-dimensional function, because it depends on both tau and f d. So, that is why it is a 2-dimensional function, a very important function in radar detection. We define it as and this should be called equation for t. Now, this actually this is called the ambiguity function, no pre-qualification of range or etc. So, this is the sometimes called radar ambiguity function. Actually, the magnitude part is generally called radar ambiguity function, because this whole integral has a phase, and that phase have some information, but we do not process that information. So, basically the magnitude of this function is called radar ambiguity function, and so I can say that to have both this resolution, because actually in measurement you want both the resolutions to be good. So, I will say that this is given a name ambiguity function. Ambiguity function. And you can easily see that this is nothing but the match filter output. So, if we just look at the match filter output for a moving target, I get this thing. So, this should be, by seeing this, by seeing the peak of this, we understand that there is a target, and detecting the next peak we understand that there is another target. So, that is detection part. Resolution part, we want that this ambiguity function should have a very sharp roll up after the peak. So, that is the choice, and for that we will see what are the candidates for that. And so, I will say that please compare equation 40 and equation 29, because equation 29 I remember actually I think we saw in the last class, last to last class, that it is the match filter output for a moving target. Compare this, and that will show that except for a phase term due to range, you have the equation 40 and equation 29 are similar. So, we can, that is why the amplitude of the ambiguity function is taken, that both the amplitudes of match filter output and amplitudes of ambiguity function, they are similar. In phase they may be different, that is why we take generally the magnitude of these. So, a peak at the output of the match filter at, let us say that if you look at the match filter output and get a peak at, since it is a two dimensional function. So, suppose tau 1 and f d 1 you get a peak. So, this means that you have a target at a delay tau 1 and Doppler shift this. Therefore, you can easily measure the range and velocity of the target. Now, all these I am saying that we have made our journey almost through, that we have seen what is the best filter for beating noise, that we found match filter, but we have found that it is not only that, it also helps us to choose the waveform, because that helps us to have the resolution. That is why I said that the choice, what is the waveform choice, that depends on what resolution you demand. So, we will further see that how to make these resolutions good, and actually there we will see that there is a problem, that if I want very good resolution in one dimension, the other dimension suffers. That means, if I want to have a very good range resolution, the Doppler resolution gets poorer or velocity resolution gets poorer, the other way around. Then we will find some technique where combinedly you can go as you like. That will be our next journey. But another thing I want to say, that throughout this, though match filter we have assumed that there is a noise, because it is against a noise we have found that against a particular type of noise we have found the match filters SNR, but the whole this ambiguity thing, that thing gets affected because there will be noise. So, according to my transmitted signal, what is the ambiguity function, then noise will change that. So, that is why the peak of the ambiguity function should be sufficiently high from the nulls of the function. If we do not have that, even if we have sharper roll up improves the resolution, but you should have a sufficient peak higher than the that what we can call the noise floor of the ambiguity function. So, that even if noise gets increased, you have sufficient margin and the target will be detected. But before going there, actually we will see that what are the ambiguity functions of various common radar pulses, and from that we will try to find out that how you can play with the waveform shape or how you can select the waveform shape, so that you can get a very good resolution. That we will take up next. So, we will start from here. Actually, the theoretical derivation is up to this. From here we will now apply one by one those things, and also after some time we will also see what are the properties of this ambiguity function, because that also helps sometimes to get an insight that what type of waveform should be chosen, etc. Thank you.